Welcome again to Let's Talk Advanced Chemistry, Chemistry 2 with Pastor Dan. We're continuing to look at solutions, and we talked about colligative properties last year. We talked only two of them. We're going to do the remaining two, so there are four colligative properties. Let's go back and define again what a colligative property is. A colligative property is the properties of a solvent, so the substance that is doing the dissolving, that has changed as a solvent becomes a solution. So when it becomes a solution, some of the properties of the solvent become different and they change. All right, now, we talked about freezing point depression. Remember, in the antifreeze, we put ethylene glycol into water solution to depress the freezing point of water so that it freezes a low temperature so your car does not become an ice box. Boiling point elevation, same thing. Antifreeze to keep the car from overheating. We also have something called vapor pressure and osmotic pressure. Now let's go through each of these. Remember, we talked about the equation there is delta to change in the freezing temperature, so it's depression going down, is going to be Kf times 1, where Kf is the freezing point depression constant, and M is molality, and the Kf is a solvent constant. So every time you change the solvent, you change your Kf. The Kf of water is 1.86 degrees Celsius per mole. We also have the boiling point elevation. That's delta T sub B. It's going up. Kb times N. Kb is a solvent constant. Boiling point elevation constant for water, that is 0.51 degrees Celsius per mole. Now for vapor point, we're going to use something called Raoult's law. I like saying that. Raoult's law. Raoult's law, we have P of the pressure of the liquid, of the solvent, is going to equal the mole fraction of that solvent times the pure pressure of that same solvent. So P sub A prime means as it would be pure. And osmotic pressure, that's the amount of energy, pressure to move through a semipermeable membrane, is expressed as pi. Pi is equal to M times R. The way we do that, PV is the nRT, V, N over V is molarity, so that's where we get M from. So osmotic pressure is molarity times the ideal gas law constant times time. All right, so, and the R is the gas constant. Well, again, those are either 0.0821 liters atmospheres per mole Kelvin or 8.31 liter kilopascals per mole Kelvin. All right, awesome. So, let's start a problem.
I said those backwards, I'm sorry. 8.31 liter kilopascal mole Kelvin or 0.0831 liters atmospheres per mole Kelvin.
At the freezing point of 255.05 grams of water, 129.65 grams of ethylene glycol dissolved in the solvent. All right, so we're going to take our freezing point, delta T sub F is equal to Kf times M. So what we're looking for for Kf, we don't know what it is. We know the Kf of water is 1.86 degrees Celsius because it's water, and we got to find the molality. So ethylene, we have 129.65 grams, and that's ethylene glycol, C2H4OH twice, and that's 62 grams in 1 mole. Divide sig figs, we get 2.0911 moles C2H4OH twice. Now we're going to take our solvent here, 250.05, convert to kilograms. Which way, the right way? That way, yep. 3 places to the left. We'll divide that through. We get 8.19288 molal. Plug that in the equation. So we're going to get 1.86 times 8.1988. We're going to make it smaller there so we have enough room. We have 5 sig figs the answer. So we end up with 15.250. Now that's
remember 1.86 is a constant, so it's not significant.
Change, and we're freezing, so we're going down. So T of F is going to be the T final prime pure minus delta T of F. So that's going to be 0 minus 15.250, which is going to be negative 15.250. So it's going to drop down to negative 15.250 degrees Celsius. All right, good to go. First one. All right, now for boiling, we do the same thing. And this one, I'm going to give you the boiling temperature and then ask you to find the mass. All right, so we have 107.855 degrees Celsius. Water boils at 100, so the change going up is 7.855 degrees Celsius. Now be careful of this. A lot of times students will just plug that 107.855 in, thinking that's the change. It's from 100, make sure you remember, or whatever the boiling point of the solvent is. So that's my delta T sub B. My equation, again, delta T sub B is equal to KB times M. We're solving for M, so delta T sub B for KB. Put our values in, 7.855 degrees Celsius divided by 0.51 degrees Celsius per mole.
We're going to have 4 sig figs because 0.51 is a constant.
Now the KB of water, we divide through, we get 15.40 mole. Now we never ever start with a concentration, remember that. So we're going to start with the 500.00 milliliters, convert that to liters.
Actually, we're going to convert it to grams. We can do that because the density of water is 1. So 500.00 milliliters is 500.00 grams. I'm going to catch myself in the video later. I'm fixing it here.
Molality, and that's of water, my solvent. Actually want grams. That should be kilograms. We should put grams and kilograms in here. This should be kilograms, just so you know. It should be kilograms. That's molality. And this should be going to grams and kilograms. And grams in there as well. I'll fix that when it comes through. All right, so when we multiply by the mass, which is 20, 19 plus 1, 20, multiply through, we get 154.0 grams of HF, hydrogen fluoride. All right, that's my answer. All right, good to go. So this one here then, determine the vapor pressure. Now remember, vapor pressure is Raoult's law. Raoult's law is P sub A is equal to XA times P of A prime. Now where are we going to find PA? Well, 30 degrees Celsius, water vapor. We should remember the water vapor chart. If we look over here, 30 degrees, water vapor chart, 31.8. So 31.8 millimeters of mercury is a water vapor part. That's my P sub A prime. All right. Now,
I'm going to pause it here. If you want to take a screenshot of that and save that for later when we do these practices, that might be helpful. So take a screenshot of that, save it, and when we go back, you can use that water vapor chart.
Defined X of A. X of A is water, so we're going to take the moles of water over the total moles. So we're going to start with water, the 750.85, 16 plus 2, because 1 times 2, 18 grams is 1 mole. That gives us 41.714. Now, if we take lead 3 sulfate, that's 702 grams is a mole.
PB2 parentheses SO4 parentheses 3 times. That's the formula.
Divide the 359.988 grams. We're just going to do the math, just save some time. That's going to give us 0.12803 moles of the lead 3 sulfate. That's where that comes from. We're going to add them together, and we're going to hit 43.227 moles, last whole column. So remember, we're going to have XA, that's going to be moles of your solvent, not solid this time, over total moles times the water vapor pressure. And this is a constant because it came from the chart. So we're going to go up 5 sig figs. Answer is 30.687 millimeters of mercury. That's my answer. Okay, now of course we got to do the last one. We have to do the osmotic pressure. So in this case, I'm giving you osmotic pressure. So we use the equation pi is equal to MRT, where pi is known to us, 0.048 atmospheres. Molarity we don't know. R, because we're using atmosphere, is going to be 0.0821 liters atmospheres per mole Kelvin. And temperature is 20 degrees Celsius, 20.0 degrees Celsius. So this is going to be 293.0. Add 273 plus 20, get 293.0. Solving for M, going to rearrange equation. Pi over RT, plug our values in. Our atmospheres cross out, so I'm going to get 1 over liters per mole, so it's going to be moles per liter, which is molarity. So we do that, we get 0.0020, only 2 sig figs because of 0.048. Now we never start with the concentrations, so we're going to start with the value. I'm just going to show you the entire work here. 500.0 milliliters, 1 milliliter is 1,000 milliliters is a liter. 1 liter is my moles, and there is a mass. Multiply through, we get 0.34 grams of ethylene glycol. That's it. Any questions, let me know. Take care. God bless. Bye.